Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Here's some more rotten stuff. I have here some newspaper, 13 months old. I've wrapped this inside and it's smelly and old. But I wouldn't trade it for a big pot of gold. I love it because it's trash. Yes, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Now look at this rest of this junk. I have a clock that won't work and an old telephone, a broken umbrella, a rusty trombone, and I am delighted to call them my own. I love them because they're trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash.
This is the song, la 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 la, Elmo's song. La 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 la, la 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 la, Elmo's song.
I like it.
La la la, la 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 la.
To think he wrote this alone.
La la la, la 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 la.
Catchy.
He loves to sing, la 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 la, Elmo's song.
Oh, sing it.
La 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 la, la 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 la, Elmo's song. He wrote the music, he wrote the words. That's Elmo's song.
Wow, that's great.
Yeah, I wish I had a song.
Yeah, but Big Bird can hear Elmo's.
How?
Well, just sing Big Bird instead of Elmo.
Great idea.
Here I go. This is the song, la 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 la, Big Bird song.
It works.
La 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 la, la 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 la, Big Bird song. La la la, la 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 la. La 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 la, Big Bird song. La 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 la, la 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 la, Big Bird song. I love the music, I love the words. That's Big Bird song. Your turn, Snuffle Pal.
All right, stand back. This is the song, la 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 la, Snuffy song.
Sing it, Mr. S.
La 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 la, la 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 la, Snuffy song. La la la, la 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 la. La la la, la 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 la. I love to sing, la 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 la, Snuffy song. La 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 la, la 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 la, Snuffy song.
He wrote the music, we wrote the words.
That's Snuffy's.
That's Big Bird. That's Elmo's song. Oh yeah!
Hi, Bert.
Oh, hi, Ernie. Hey, I've been sitting here trying to think of what we could do with this here letter L.
Oh, well, let's see. You know, one thing you could sing sort of a la-la-la song with the letter L.
What do you mean?
Well, there are all kinds of pretty words that begin with L. You know, you could sing a few la-la-las and some pretty little words and you'd have a nice little song, you know,
La
Bert?
la la, like that?
Sure, go ahead. Try it.
Okay, let's see. La 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 la, lemon. La 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 la, light bulb.
Uh-huh.
La 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 la, lamppost. This is fun. La 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 la, lump in my oatmeal.
Well, that's not quite what I was thinking about, Bert.
No?
I mean, there are a lot of pretty L words, and I was sort of thinking of the ones that are more lilting and lovely. You know, like la 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 la, laughter.
Oh, yeah, I see.
La 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 la, lullaby.
Like that, huh?
La 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 la, lollipop. La 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 la, lights in the sky.
Oh, Ernie, I got a great L word. This is a beauty. Oh, listen to this. La la la, linoleum.
No, Bert, listen to me. 'Cause L is such a lovely letter. For words like licorice and lace, the letter L lights up your face, so why not la 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 with me?
Fraggle Rock.
Sunny day, sweeping out clouds away. On my way to where the air is sweet. Can you tell me how to get to Sesame Street? Come and play, everything's A-OK. Friendly neighbors there, that's where we meet. Can you tell me how to get to Sesame Street? It's a magic carpet ride. Every door will open wide to happy people like you. Happy people like, what a beautiful sunny day. Sweeping up clouds away. On my way to where the air is sweet. Can you tell me how to get to Sesame Street? 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 How to get to Sesame Street?
Well, good morning, everyone. Welcome to the BERT Masterclass for the HSMA program. So this one's been a little bit of a long time coming, but hopefully this will be a nice little introduction to natural language processing, the use of BERT for natural language processing. And we'll touch on a little bit the fact that BERT has, although it was originally developed for natural language processing, has actually much wider applicability, and is used, these transformer-based models are actually used all over the place. And we'll talk a little bit about that, but we're focusing today on the application of these transformer-based models, specifically BERT, the one that really changed the landscape to this day for natural language processing. Now, as you probably saw, as we talked about in the Slack chat a little while ago, one thing to flag up right from the off about BERT is training, or as we call them, fine-tuning BERT models. We'll talk a bit more about what we mean by that in a bit. Actually requires quite significant GPU resource. You need CUDA-enabled GPUs or a TPU of some kind. So obviously most of you, if not all of you, probably don't have access to that, at least not locally. Obviously there are options to run in things like Google Colab, and we'll talk a little bit about that as well today. But the stuff that you're going to be doing today is not training the models. You will have some pre-trained models and you'll be playing around with some of the aspects of BERT. But just be aware that if you are using these things for real, then you're likely going to need to be doing some fine-tuning, and you will need to think about how you will do that, whether that's trying to use it as a justification to get a brand new GPU, or to think about an online cloud service that would allow you to train these models. But even on very fast computers, so I accidentally, as you know, I've got a very top of the line computer now, and it has a very good GPU in there, and it also has a very good array of CPUs, but I accidentally went into the CPU instead of the GPU last week when I was checking out some of the code, and you can tell. So even on a very fast CPU setup, if you're not using the GPU, you will be taking potentially days to train something versus minutes or hours. So it's that much of a difference. So it's really important that you're aware of that right from the off, that these things are designed to run on GPUs. If you're training them, once they're trained, as you'll see today, you can apply them without that. But the training does require that. But as I say, today for the training session, we're not going to get you to be doing any of that. Even if you had all access to GPUs, the training would still take a non-trivial amount of time, and it's largely pointless for what we're trying to do today. So today is basically going to be an overview, bit of an introduction to BERT, where it came from, and how it works. BERT is pretty complicated, so I've tried to make this as accessible as possible. Transformers are not the easiest things in the world to understand, but hopefully I've managed to break it down. Certainly there are, and I will direct you to various resources that I used to help me understand BERT many years ago, when I probably around sort of 2018, 2019, when BERT was still new. There was scant resource out there, and it was directed at very, very technical people, and I struggled to learn BERT at that time, and walked away from it because it was almost impenetrable to understand. It's now matured. It's so extensively used now. There are now some excellent resources out there to help you make the sense of this. There's also the original BERT paper, which we can link to as well, which is where they introduced the BERT model. So with that in mind, let's plow on, and let's introduce the world of BERT. If I can advance my slides. What's going on here? Oh, sorry, having technical difficulties. I lost my cursor. There we go. For some reason the slide won't advance. Oh, there we go. No, we don't want that again. Right, okay, there we go. So as I mentioned, BERT's not an easy thing to understand. This particular tutorial here, what has happened to my sorry, I'm just going to I'm just going to close this down and then start the slideshow again because my cursor keeps disappearing. It's really annoying when I'm trying to point to stuff. Let's try it again. There we go. That's better. I think it's Zoom. There are a few weird things in the newer Zoom apps on Linux. Anyway, yeah, so I mentioned there's a few good resources. This is the one in particular that really helped me understand how BERT works. It's very easy to follow, and well worth checking out that particular link, as well as this one as well. So the Towards Data Science one, which uses a lot of the forms the basis for the code that I'm going to be talking through later as well. Sorry, not that one. It's the data camp one, which will form the basis of the code that we're going to look at, because it gives an example looking at sentiment analysis, which is what we're going to do today, using some of the data that you've already seen earlier in the course. But all three of these are well worth reading. The data camp one walks you through code, which is what we're going to do today. But these two links up here as well are more of a general, fairly quick read introductions to BERT. So don't be afraid to check those out. It's not a thing that's immediately going to sink in your heads. It's not an easy thing to understand. Okay, so first of all, what is BERT? It's clearly some kind of acronym. And it is indeed. It stands for Bidirectional Encoder Representation from Transformers. Don't worry, we're going to unpick all that. But that's what BERT stands for, and it's basically a machine learning model that was developed by Google back in 2018, 5 years ago now. And basically, BERT has completely transformed, no pun intended, the world of natural language processing, and I'll show you just how much it is, because you probably won't realize how much you are interacting with BERT on a daily basis, and so much so that many of the things that we demonstrate early in the course, those kind of things are quite outdated now. Not Spacey is widely used, but a lot of the kind of approaches of in the sentiment analysis training of building that up by hand, it's quite an outdated way of doing it, because BERT and the other similar models that have come since have completely just blown the stuff out of the water, both in terms of kind of the performance and also just the way in which you can understand context from text, which is what we're going to be talking about. And as I say, you've probably all, in fact, you will have all interacted with BERT and will be on a daily basis. You may well have done so today without you knowing it. So we're going to be introducing BERT today. We're going to talk about how it works, and I'm going to show you an example of a BERT in action. So what can this BERT thing be used for? Well, basically, pretty much anything in natural language processing, so huge ranges of stuff. So things like sentiment analysis, which obviously you're familiar with from earlier in the course, can be used for named entity recognition, which again you're familiar with earlier in the course, generating natural language text, answering questions, all of those big NLP tasks that we're aware of. All of these things, BERT can do it. Okay, and it's so flexible being able to do it. And we'll explain more about why it's so flexible. And as I say, today we're going to be focusing on the sentiment analysis bit, because that's the bit we directly looked at. But don't just think this is for sentiment analysis; it can do all sorts. And the fundamentals of how a BERT model works are basically how it unpicks language, and then it can be used for anything else. But we're going to look at sentiment analysis. We're going to look specifically at exactly that same movie set data that we used in the sentiment analysis training back in phase 1, but we're going to compare using a BERT model compared to what we did back then, which was basically building our own little neural network from scratch. Now, BERT and transformers in general are all about the concept of context. Okay, this is the key power of language models like BERT, is that they can understand the context of text, and we'll come back to this a bit more in a moment. But one way in which you will be interacting with BERT on a daily basis is via Google. Google uses BERT in its search engines now. What's quite interesting is that, so this is the kind of before BERT, when you typed something in to Google, let's say you typed in, can you get medicine for someone pharmacy? Pre-BERT, you would have got a link maybe like this about getting a prescription filled, but it hasn't really captured the context of what you're really asking is, how can I get it for someone else? That's what you're asking. Post-BERT, BERT understands that context, and so you'll get more likely a link like this. Can a patient have a friend or family member pick up a prescription? Okay, so it's actually understanding. It's not just a bunch of words. It's understanding the context and trying to understand what you're actually saying there. It actually throws me off because I'm so used to so many years of the pre-BERT world that you know, I still search on Google using key terms and not proper sentences like that. But actually, that's the optimum way to search now, because it's using BERT, and BERT will understand the context and will actually be able to give you links to try and answer that question. And you can read more about this example and others at this little blog here as well. So BERT's an example of what's known as a large language model, and these are basically models that have been trained on extreme volumes of data, so huge corpuses of text, and they can generate and understand natural language really well because of that, and because they've got a transformer-based architecture. Okay, and that's what we're going to talk about in a moment. So GPT-2 and GPT-3, upon which ChatGPT, which you're probably all familiar with by now, ChatGPT sits on on the GPT-3 model. It's basically, ChatGPT is just the chatbot interface with which you interface with the GPT-3 model. It allows you to converse with it. Okay, but underneath is a large language model like BERT. That's what's powering it. The chat bit is just the chatbot bit, the interface that you use to work with the model. Now, the original, just to give you an idea of how vast these things are, so the original BERT model, and there are many now, as we'll touch on later, was actually trained on 3.3 billion words, and it was all from Wikipedia and from Google's book corpus. So huge volumes of text data that this stuff has been trained on. Okay, so this is part of the reason why they're so good. They've seen so much, but there are drawbacks to that, and we'll touch on that later as well. Okay, so we said that BERT stands for Bidirectional Encoder Representations from Transformers, which doesn't seem to make much sense at first glance. So let's start to unpick that to get to the heart of how BERT works. So let's start with the first word we've got here, bidirectional. So to understand what we mean by bidirectional in the context of BERT, we need to understand that BERT uses something known as MLM, or masked language modeling. Okay. So to try and understand what masked language modeling is, we're going to play a quick game of That's right, we're going to play blankety blank, because this will explain to you what masked language modeling is, hopefully. Okay, so for those, hopefully most of you are familiar with the game of blankety blank. If you're not, I will briefly explain it. Essentially, it was a TV show that ran for many, many years, and was brought back in a number of reboots over the years as well. But the principal ideas remain the same. You have a panel of 6 celebrities at the time, and 2 contestants. Each contestant plays. They are given a sentence which contains a blank. And the panelists, the celebrity panelists, write down what they think should be the missing word, and the contestant does the same, and the contestant gets a point for every time they agree with one of the panelists. Okay, so if they fill in the blank word in the same way. So we're going to play a version of this using actual questions from historic blankety blank shows. And basically what I'm going to ask you to do is I'm going to give you the sentence with the blank, and I want you to put in the chat what you think the blank is, and then I'll tell you what the contestant gave as the answer for that particular one. Okay, so here's your first one. Delilah cut off Samson's hair to sap his strength, but I just heard that first she cut off his blank to slow him down. So Delilah cut off Samson's hair to sap his strength, but I just heard that first she cut off his blank to slow him down. What do you think the blank is? Put it in the chat.
Blankety blank, 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 blankety blank.
Okay, let me bring up the chat. Would help because it doesn't notify me on here now. Let's see. Right, so we've got eye, feet, legs. Yeah, legs seems to be quite a popular answer. Feet's pretty close. Let's have a look at what the actual answer was. My answer in this case, my answer was legs. Delilah cut off Samson's hair to sap his strength, but I just heard that first she cut off his legs to slow him down. Okay, let's try another one. My partner cooks for me every night. It's not that I don't appreciate the effort, but I wish they knew how to turn the blank on. Off you go.
Blankety blank, 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 blankety blank.
Okay, let's have a look at the chat for this one. Let's see what people have come up with. So, my partner cooks for me every night. It's not that I don't appreciate the effort, but I wish they knew how to turn the... Somebody's put TV, oven, microwave, oven. So oven seems to be a popular answer. Let's have a look and see what the answer was. Indeed, the answer was oven. So well done. Okay, so why are we playing blankety blank? Well, basically, a mass language model is one in which that has been trained to predict a masked or hidden word in a sentence, given the context of the words surrounding it. And it does that by essentially looking in both directions from the missing word. Okay, so both before and after the missing word. And that's what we mean by bidirectional when we talk about BERT being bidirectional. So the words selected to be masked are typically random, and they will be a percentage of the total words in the training corpus. Okay, so in the case of BERT, it's 15% of the words are masked during training. So it randomly hides 15% of the words that it's trained on. And it basically says, go on then, what do you think that word is? Okay, so it's basically playing blankety blank, and you just did that when you played blankety blank. So when I gave you this sentence, Delilah cut off Samson's hair to sap his strength, but I just heard that first she cut off his blank to slow him down. So let's look at that. So essentially, BERT would look at the stuff before the masked word. She cut off his hair, i.e. part of the body, to sap his strength, and also cut off something else. That's the information I'm getting from this. After the missing word, the something else that she cut off was to slow him down. So putting that information together, we know it's a part of the body that would slow him down, and therefore we're going to conclude it's probably legs. Okay. Similarly, for the second one, if we look before the blank, that we know that the partner cooks every night, but there's an indication that it's not entirely without issue, because they don't know how to turn something and then post the masked word. It's turning something on. So it's something they need to turn on to cook, and it seems to be there's a possible note of sarcasm in there. So it might be something basic, and we conclude that it might be oven. Okay, so this is basically what masked language modeling is. It randomly puts in a blank and looks at the stuff before and looks at the stuff after and tries to predict what it thinks the missing word is. So whenever you think of masked language modeling, just think blankety blank, and it's basically that. Now, of course, as well as all the times that we all play blankety blank with friends, surely at least twice a week, we also do this beyond that in our everyday lives. In general conversation, we do masked language modeling. If we don't hear something, particularly as I get older, I'm finding that happens more often than not, we try and fill in the blank. We try and work out what the person said, what that missing word is, the word that we missed. Or when we're reading, sometimes we read quickly, and our brain is essentially doing the work of filling in the blanks. We're skipping over stuff, and it's filling in stuff. And sometimes that can work against you. You can read stuff too quickly, and you filled in blanks that aren't there. But of course, as just like a masked language model, when we do this, or indeed like a blankety blank panelist, we won't always predict the word correctly. They are just predictions. Okay, so BERT is making a prediction about what the missing word is, but it won't always get it right. Now, you can actually play around with the masked language modeling bit of BERT using the API at this the following link. I've also given you the code which you'll be playing around with in the exercise, where you can do it locally, but you can also do it without installing anything on this particular link here. And basically what it allows you to do is interface with the masked language modeling bit of BERT. And it allows you to put in a sentence, and you can mask part of it out. In other words, put in a blank, and you do that using this mask token, where you put these square brackets around the word mask in capital letters. And you can see what BERT will predict to be the missing word based on that. And it'll give each word a level of confidence. Each prediction will have an associated level of confidence for each of the top 5 answers. So I assure you I didn't do this multiple times just to make the point, but I typed in just randomly, everyone agreed that Dan was the mask teacher they'd ever encountered. Obviously if this was on blankety blank, what would they come up with? Oh look, it's 80% confident the answer is best. Wow. The next top answer was worst, although that was only that was a much lower level of confidence in that. Otherwise it might have been greatest, finest, strongest. I would accept 4 out of 5 of those. Okay, so it's basically just been given this sentence. It's got a masked word here, and it looks at what came before and it looks at what came after, and BERT then makes a prediction about what the missing word is. It's playing blankety blank. That's what masked language modeling is. Okay. So as well as masked language prediction, blankety blank as we now think of it, BERT is also trained on something called NSP, which is next sentence prediction. And basically in next sentence prediction, the model gets shown a pair of sentences, and in half, so it gets shown sets of these pairs of sentences. In half of the pairs of sentences, the second sentence correctly follows the first sentence in the pair, but in the other half it doesn't. So for example, let's have a look at a correct sentence pair. Dan bought a new computer. It was much faster than his old one. Okay, so this is a correct sentence pair because this second sentence follows on from this first sentence. So it'll have 50% of the sentence pairs it looks at will be correct sentence pairs like that. And in the other 50%, there will be an incorrect sentence pair. So here's an example of an incorrect sentence pair. Dan had a late lunch on Tuesday. Donkeys are not native to Canada. Okay, that second sentence doesn't appear to follow on from the first sentence. Okay, so next sentence prediction is basically where you try and predict, does this given these sentences, does this second sentence follow on from the first sentence, yes or no? And that's what BERT tries to work out. Okay, And basically, BERT is trained on these two things, masked language modeling and next sentence prediction, and it's split 50-50. So half of it is on playing blankety blank, half of it is trying to predict correct sentence pairs. Something worth flagging up here when we use sentence pairs. So in this example, we've got a single sentence followed by a single sentence. You'll see when you come onto the exercise that you can actually have, slightly confusingly, multiple sentences as the first sentence in a pair. Okay, BERT accepts that. It's basically a stream of text followed by another stream of text. Does the second stream of text follow on from the first stream of text? But we call it next sentence prediction. Okay, so those are the fundamental ways in which it learns. Okay, blankety blank and next sentence prediction. So when you break it down like that, it's actually quite easy to understand. It's trying to work out, it's blanking out words, trying to work out what the missing word is, and trying to work out if one sentence correctly follows on from another or not. But how does it do all that? What is the mechanism by which BERT learns? So let's next turn our attention, and my goodness, you're going to be laughing about that by the end of this session, that fantastic joke, to the transformers bit of the acronym. So remember, BERT stands for Bidirectional Encoder Representation from Transformers. We now know what the bidirectional bit means. In the context of BERT, it means looking in both directions out from a masked word. Okay. What do we mean by transformers? Well, we touched on transformers a little bit earlier in the course when we looked at spacey. We explained a little bit about how spacey worked, but we're going to talk about it in a bit more detail. But we're also going to refresh a little bit on what we did in that particular course. So you'll hopefully remember this, but when we talk about transformers, we first need to learn about the concept of attention. As I say, we talked about this earlier in the course. Were you paying attention? My goodness, this slide is full of excellent checks. So let's remind ourselves, if you had a look at these slides, as I say earlier in the course, let's study this following paragraph. My cat is called Prince and he's very demanding. Every day he asks for his treats 11 o'clock, his 11s is. You could set your watch by him, so accurate is he in asking for them on time. Sometimes when I'm teaching, he has to wait for them and he gives me a look that he's clearly not happy about this. Okay, so let's have a look at the concept of attention. And it's something that we do as human beings without really thinking about it. Okay, because when we read or hear a paragraph like that, we relate the things that we read or hear back to stuff earlier. Okay, so I said here, my cat is called Prince and he's very demanding. So I know that the he that I'm referring to here is Prince, my cat. In the next sentence, every day he asks for treats. I'm still talking about, I know I'm talking about my cat Prince. His 11s is. You can set your watch by him. I know all this is referring to Prince, and even down here, he has to wait for them and he gives me a look. We know that I'm talking about my cat Prince here. Similarly, the ones in green here, he asks for his treats, which are his 11s. We know that the 11s refers to the treats. When we talk down here about asking for them on time, we know that them refers to the treats. Okay, and similarly down here, where we set in the blue, he has to wait for them, and he's clearly not happy about this. When we say he's not happy about this, we know that the this that he's referring to here refers to the fact that he's having to wait. Okay, now this sounds very straightforward, and you might think, well, so what? Yeah, of course that all makes sense. That's not how language models worked pre-BERT. Okay, basically the old convolutional neural network approach to natural language processing doesn't allow for that. So this is how things were done pre-BERT. Okay, basically the way they would work is it would look at a bit of text at a time. Remember, it's a bit like a convolutional neural network, is a little bit like a sliding window. So it's got this little window and it's scanning over the text bit by bit. And because it's looking at the text bit by bit, and it's looking at a portion then sliding on, the closeness of the words to the thing that you're trying to classify or predict becomes important, and arguably it becomes too important, because that means it becomes very poor at identifying long range dependencies, i.e. words that relate back to things earlier in the text. So back here, by the time we get down to here, if we've got a little sliding window of say 5 words, by the time we scroll down here, we have no idea what he refers to. We've forgotten that because our window has moved on. Okay, it's the only things that he refers to here are these little words around it, and that's how the old model worked. And that's a problem because natural text, as we've just seen from that example, is full of the issue that you need to be paying attention, that things will refer back to things said sometimes some time ago, and we don't keep repeating ourselves. I don't say in this thing, my cat is called Prince and my cat Prince is very demanding. Every day my cat Prince asks for treats at 11. We don't talk like that. Okay, so that's not natural language, but that's the way that the old approach would need us to be talking or communicating in order to work properly or to work effectively. So what's the alternative to this? Well, the alternative is to use the concept of attention. So basically, with attention, we put portions of text against each other in a matrix. Now we'll deal with just 2-dimensional matrices here because that's easier to conceptualize. But of course, as with all these things, imagine it then in multiple dimensions. But essentially, we can put them against each other in a matrix. And for obvious reasons, that's used extensively in translation. Because you can put the text with each word in English along one axis and then say in French along the other axis, and you can then identify the relationships between those words, and then make this a very effective way of translating from one language to another. But there's a nice little thing that you can do, which models like BERT use, known as self-attention, which is rather than put 2 different pieces of text on each axis, we can put exactly the same text on each axis. So exactly the same, if we had that paragraph before about Prince, we can put that on one axis and then exactly the same on the other axis. And we can then use that to identify the relationships of words to other words within the same piece of text. Okay. And that's starting to get us towards this concept of that word. When I say him down here, I think I mean Prince up here. And you can identify the strength of the relationships between words. And that's basically emulating exactly what we're doing as human beings when we're reading some text. So let's also think about another example here. Think about the following sentence. John asked Mary if he could borrow her pen. Now, as human beings, it's probably likely that when you read that, you will be assuming that the thing that John wants to borrow from Mary is some form of writing device. It probably doesn't want to borrow a female swan or an animal enclosure. But of course, they both have the same word. We use the word pen for all 3 of those things. Sometimes additional text can help us understand the context as well. This is because John was busy writing his memoirs. Oh, okay, must mean pen then. But also because you don't tend to borrow a swan. I don't anyway. Maybe I live in a different world. I don't tend to borrow many swans or indeed animal enclosures. So when we see John asked Mary if he could borrow her pen, we probably essentially we're doing what BERT does. We are making a prediction. We're saying probably means a writing implement. We're doing that so sort of unconsciously that we're unaware of it, but that's what we're doing. Now, of course, in natural language, the same word can be used in different places in the same text, even to mean very different things. Okay, and this is known as polysemy. And the thing that helps us understand is the context of the word in the sentence or wider text. So as we just saw, the fact that John wanted to borrow this pen from Mary indicates it's something he wants to borrow, and that's probably the pen. And indeed, if as a writing implement, if we had that second bit of the sentence about writing the memoirs, we'd probably be even more confident that the sentence was referring to a writing implement. So we're getting clues from within the text and external to it, things that we've seen before, things as we learn as human beings, but things that also BERT has gone out and seen from its 3.3 billion words that it's trained on, its vast corpuses of large text data, stuff that it's seen. It knows probably that John wants to borrow a writing implement. So that's attention and context. So what do transformers do? Transformers tie this together. So transformers basically use the concept of attention. This concept that you can link, relate words, or specifically it's using self-attention, but we just typically call it attention, where you're putting the same text against itself and modeling the relationship between words within the same piece of text. And we use that to try and understand context within our text. And then basically what transformer will do is it will encode that context information alongside the word. So that's what transformers doing. So unlike the old approach, the old convolutional neural network approach, where it's only looking at this kind of sliding window and it's just looking at the context of words based on the words that immediately surround it, given, I mean, you can have quite a large proximity, but you know, it's still only able to do that. And of course, there are drawbacks with extending that window as well. Whereas a transformer can pull in information from anywhere in the text, so not just your defined little sliding window. It can pull it in from anywhere to try and understand the context of the words that it's looking at to make a prediction. And that makes them incredibly powerful for tasks like natural language processing, but as I touched on earlier, also for so many other deep learning tasks as well. But originally designed for natural language processing, and hopefully you can see why they're so powerful compared to the way things were done before. And it may be a surprise to learn that's how things were done before, and it's almost remarkable that that worked as well as it did. But things like BERT works so much better, this transformer-based architecture. That's why they're so powerful, because it can draw in that context and is much more representative of how natural language actually works. Okay, so we've talked about bidirectional, looking both ways, blank to blank. We talked about what transformers are doing. They're basically using the concept of attention or self-attention to encode context information alongside words in text. So we know that they're doing that. We know our transformers are doing that, but we also don't want them to link up everything, because most things won't matter. If you had a huge, let's say you're looking at, I don't know, a novel, you're not going to want to link every single word in that novel with every other word in that novel. It'll be huge. And most of the words won't relate to most of the words in there. We just want to focus in on the things that are important or are likely to be important. So the way we do this is by using weights. So just as we've seen when we've looked at neural networks before, this concept of using weights to identify how strong a connection is, how important something is. And weights are used here to identify which aspects, so in natural language processing, that's words in our text, are most important. So which are the relationships that are most important in the attention mechanism. And the way in which BERT does this is using an encoder. So this is what we mean by the encoder representation bit of the acronym. So just before I explain a bit more about that, there's a nice little link here which explains what encoders and decoders are in the context of transformers, and I use that as a nice little reference point. So it's well worth checking that out. It's very easy to read, and it's got some nice little diagrams too. So basically, in a transformer, what an encoder does is it takes some raw text input. I say raw. It will have been pre-processed in some way, and we'll see that later when we look at the code. that, and we remember back from our natural language processing training, remember computers have to deal with numbers at a fundamental level. The same with neural networks. We can't stuff words through them, we have to stuff numbers through them. So the words are converted into integers by some sort of pre-processing model. We'll touch more on that. But you've seen a bit of that in the natural language processing training before, where we convert words into numbers in some way. So it's, when I say raw text, it's taking raw text as numbers that have been pre-processed a bit. So it's taking those, the encoder takes those in as an input and extracts from that features from the input text. So the output of the encoder are various features, and we'll talk about a bit more about what those features are. But in most transformer models, such as BERT, the encoder isn't a single encoder, it's actually a number of encoder layers, and the output of the final one represents the features. So these have quite complex architectures where you've got lots of these networks, these encoder networks, that are flushing through all this text data as numbers, and then the kind of final output out of that stack of networks, encoder networks, will be the features of the text. And specifically in BERT, the features that are extracted include the self-attention structure, the thing we talked about before, that matrix of, it won't come out as a matrix, but it's that essentially the weights of how important this word is related to this word. So it'll identify the things it's learning are these words are linked to these words, and that allows it to determine these weights for the self-linkages, and that allows it to work out context. It's also worth flagging up that there is something as well in a transformer model known as a decoder. And basically what a decoder does is it takes the outputs from the encoder. Remember, the outputs are the relevant features of the text that have been extracted. And it uses that to generate a text output. Okay. So the encoder has taken in the text and said, these are the relationships between the words, these are the, essentially this is your raw context information. The decoder then takes that and then uses it to generate some text, some actual readable text. So you can use a transformer to undertake translation using this setup. So you can feed in text in one language, language A. Let's randomly pick the text down is amazing. We feed that into our encoder. The encoder then unpicks the features of the text, including the context information. That then goes into the decoder, and the decoder will spit out the text in another language. If we're using this for that's how we set it up. And so then we have the translated form of Dan is amazing. Okay. So obviously you can get your decoder to do whatever you like, but that's how you could use it for translation. But just to flag up, BERT doesn't use a decoder. It just has an encoder. Basically, it's a pre-trained model that doesn't generate the outputs out of the box. We bolt that on. Okay, so BERT does this bit, and then we decide, we use that context information to then apply it and bolt on our own thing after that, using those outputs to say, okay, I want to do some sentiment analysis, I want to do some named entity recognition using that vast context information that you've learned. Okay, and that process is known as fine-tuning, and that's what you're going to have a little bit of practice with playing around with today. Not the fine-tuning itself, because that's the bit that you would typically train and will take a long time if you're not using a GPU. But you'll see some of the outputs of that fine-tuning training. We'll talk a bit more about fine-tuning. So what do we mean by this fine-tuning? So basically a BERT model, and there are many, there aren't just the original BERT model, although that's the one we're going to look at and be using today, the original BERT model. But there are lots of different BERT models that are out there now, and you can actually, I've got some links that you can explore some of those different BERT models. Some of them have been trained on different corpuses of text, which make them more useful for different applications. But basically, a BERT model is pre-trained on large corpuses of data. That's always the case. Excuse me. And it's able to predict the context data of text using the encodings that it learned during training. So it's really important that it's pre-trained, because training a BERT model from scratch is extremely computationally expensive. Remember, the original BERT model was trained on 3.3 billion words from Wikipedia. You don't want to be doing that every time. So you essentially use a pre-trained BERT model, and then you add to it for your particular application area. Okay, so we take all of that training that it's gone out and learned, and we apply this what's known as fine tuning. So we get the original pre-trained model, and we tune it to our particular problem area and our particular application. So as we're going to look at today, that is the sentiment analysis of movie reviews. Okay, but we can use that same BERT pre-trained model to extract named entities from patient surveys, or to serve as the basis for our chatbot. It's the same BERT model, pre-trained BERT model, but the fine-tuning will be different. And we can do this in different ways, the fine-tuning. We can either fine-tune ourselves, or you can actually use one of the many free and open source pre-trained models that are already fine-tuned for certain tasks. So there are models that people have put out there, things like Twitter sentiment analysis. So this link here, that's a little model that you can use straight off the bat. If you want to do some sentiment analysis on Twitter, you could choose to use this model. You wouldn't have to do any training at all. And you could just use that model for your data. Or there's one here on toxic comment detection. Okay, there's lots and lots. In fact, if you go to this link here on Hugging Face, there are over 220,000 models at the time of presenting this. Just be aware that you can put anything up there. So there is no kind of quality control. So just be aware of that. There may be absolute rubbish up there. So you might want to investigate how people, how much these things are being used. And you might have something that sounds really good, but is actually pretty useless. So just be aware of that. Don't just think, oh, I can use that without questioning it. You also need to be looking at how it works and how it's been trained, and asking questions as a critical consumer of that model about whether you should be using it. But you can grab these things off the shelf, and there are lots and lots of different things out there. So it's well worth looking. If you've got a particular problem, you don't have the GPU resource to fine-tune your own BERT model, you can have a look here and see if there is a decent model that might work, and try it. You might find something that's very similar, and it might work quite well for what you're trying to do. So it's well worth having a look at that. And some of the stuff, particularly around Twitter sentiment analysis, is quite a common thing. So there will be well-established models that can do that kind of stuff. But in the example we're going to look at today, I basically fine-tuned my own model. So I'll talk you through the code that allows you to do that. So as I mentioned right at the start, the original training of a BERT model is incredibly computationally expensive. But even though you don't do that, or most people don't do that unless you're creating a brand new BERT model, you are likely going to be doing some fine tuning. That's what you're more likely to do, unless you can grab something off the shelf that works just as well. Remember, this is only practical, and I do mean that this isn't, oh, it'll run much nicer. This is it. It will be impractical if you don't do this. You have to have access to either a CUDA-enabled GPU, a graphics processing unit, or a TPU tensor processing unit. If you've got one locally, great, and I would strongly advise you use it. If you don't, then there are cloud options, things like Google Colab. Now, Google Colab has a free tier, as you've used before, and you can access GPU and TPU resources on that. It's if you're not paying, it is at best unreliable. because you are down the chain. You will get deprioritized. You may get cut off at any moment, which is particularly annoying if you're training a large model. If you're doing this properly in earnest, I would advise, and you want to look at a cloud solution, you may want to consider paying. I have to say, looking at the Google Colab tiers, it doesn't sound too expensive initially, but it's all designed to make you spend money. Of course it is. You get an initial. If you got to the next tier, I think you get so much time access to GPU. So when you still don't get to choose which GPUs, and there are a vast range of different spec GPUs on there. But you do get some more of a priority access. But actually the time you get isn't huge if you're doing a lot of this. And of course, beyond that, you can of course pay to top up your time, and it's quite expensive. So just be aware of that it can soon mount up if you're doing this in earnest. But the key message here is, if you're going to be fine-tuning BERT models, you're going to have access to a GPU. There is no getting around that. You will not be able to fine-tune a BERT model. You can take a pre-trained BERT model and then take a pre-trained fine-tuning model, bolt the two, and use that. This is essentially what you're going to be doing today. You're going to be taking my fine-tuned model that I've given to you. You can do that on very limited resources, but if you need to train something, if you need to fine-tune something, you're going to have access to a GPU. So just be aware of that. Okay, so that was a lot of information to take in. So let's try and summarize what we just talked about, how BERT works. So BERT models are pre-trained on huge amounts of text, and they're trying to understand the context of text using this concept known as self-attention, where you're trying to relate words in the same text to words within the same text elsewhere. And the way they do that is to use an encoder mechanism from transformers without the decoder bit. Okay, so it's just using the BERT's just using the encoder bit. And encoders take in pre-processed text as numbers. They extract features, which are things like self-attention weights, and they spit them out the other side. BERT will use multiple layers of encoder, where it's bringing in raw text as numbers. Raw text goes through a pre-processed model to turn it into numbers and stuff. That pre-processed text then goes into the encoder, goes through multiple layers of network, and then spit out the other side are the features. And that's the bit when you go to fine-tune, that's the bit you start with. BERT models are trained using a combination of next sentence prediction and masked language modeling, blankety blank. By doing these things, it gets good at extracting the attention features from context features from text. And because BERT models take huge amounts of computational resource and time to learn, so what we do is we first take a pre-trained BERT model off the shelf, and then we use that initial pre-trained BERT model, which has all that valuable context information that we're going to need, and then we fine-tune it for our particular application and problem area. So in today's example, that will be determining the sentiment of movies. And we do that either by building and training our own, which will need some GPU resource. So we bolt it onto the pre-trained BERT model. We take, in the example today, take the original BERT model, bolt on our fine-tuning model for learning how to correctly predict sentiment from movie reviews. Or we can also grab one of these fine-tune models off the shelf as well, if there's something that works well and has been already developed. So this is the basic flow. You have your BERT model here, that's pre-trained. None of you, I suspect, will ever be training a brand new BERT model. That's a big undertaking. That's training something. You might, but typically you'd grab that off the shelf. So you have your pre-trained BERT model, which has this encoder representation. And then we use all that valuable context information. We bolt on a fine-tuning model, either one that we develop ourselves and train it ourselves, or one that's already pre-trained. and then we use that for our final model implementation. Okay, so that's basically how it works. Now, before we move on, it's one thing just to touch on really, and it's quite an important point. And you'll remember we touched on this a little bit when we had our ethics in AI session back in phase 1, and we talked about large language models like BERT in particular that are going out there. You've just heard that BERT was trained on 3.3 billion words out in the wild. And it learns from all this huge amount of text data. That also means, unfortunately, that it's soaking up all of the rubbish that's out there too. And there's a lot of bias and unpleasantness out on the internet, unfortunately. And in fact, just to demonstrate this, we're going to have a look at a bit of bias in action. So I'm going to use a simple piece of code which I've given to you, BERT-MLM.py. We could also use the online tool that, from Hugging Face that I mentioned earlier as well. I'm just going to use the Py file here. So if I switch over to this, and you'll have a chance to play around with this in a moment as well. So basically what we're going to do here in this BERT MLM is, I mean, there are 3 lines of code here. Most of it is just comment. So this is a way in which we can get access to the masked language modeling bit of BERT. Okay, so the blankety blank bit. Okay, we can access that. So from transformers, we import pipeline, and that basically will give us a simple API that will allow us to then use 2 lines of code to make some next sentence predictions. So this first one here, what this line of code does here is it sets up what's known as an unmasker pipeline. Basically, that just allows us to get into BERT's masked language modeling predictions, that bit of its training for a given sentence. So this is where we play blankety blank. And what it'll do is it'll give us some predictions about what we blank out a word in our in text, and it'll give us some predictions about what the missing word is with descending levels of confidence. The model we're going to use here is BERT base uncased. Now, I said there are lots and lots of different BERT models now that have been trained. These, remember, that's different to the fine-tuning models. These are the big BERT models. BERT based uncased is the original. That's the original BERT model that was trained. So that's always a good starting point. But there will be models that have been out there that have been put out there that have been trained in other areas as well. So the uncased bit of this original BERT model basically just means it ignores whether the letters are capital letters or lowercase. So it would be down with a capital D and down with a lowercase d as being the same word. It's typically what you want with these kind of models. And you can read a description of that model, the original BERT model, obviously in the original BERT paper, which I'll link to later, but also here. So if you click on that, I'll do that now, click on that link. This will describe BERT base uncased, which is the original BERT model, and describe how you can use it. And you can see there are different ones here. There's BERT large uncased, which is a larger version of it, BERT base cased, where you do want it to differentiate between capital letters and not capital letters, etc. But we're using the original one here. So that sets up an unmasker pipeline, basically peels back imagine you're a surgeon, you're making the incision, peeling back to get access to the training pipeline, the masked language modeling bit of the training pipeline. Now all we need to do is apply the unmasker pipeline to some text. That's it. That's all we do. So we import, set up the pipeline, and then use the unmasker for text. So all we do is we pass into unmasker some text, and we use the token mask, so capital letters around mask and in square brackets. And what it'll do when we run that is it'll provide us with 5 predictions of what it thinks the missing word is, just like we played blankety blank earlier, in descending orders of confidence. It will look for punctuation too. This is quite important to note. So if you miss a full stop, let's say if I took that full stop out there, it might, perhaps not in that one, but it might predict, one of the predictions is a punctuation. so it can predict punctuation. So just be aware of that when you're trying this yourself. You can only mask out a single token. Okay, so just like blankety blank, you can only have one blank. So let's have a look. So the first example I've got here are the cats are generally very mask. Let's see what it thinks the missing word is. So let me just in the way there. Let me run this. Take a second to kick in. Here we go. Right. So for that particular sentence, here are the 5 words along with the scores, and they are descending. So the top one is the one it's most confident about. The one it's most confident about is intelligent. Cats are very intelligent. Then it thinks large is the next most likely, then shy, then small, then tame. So it thinks the most likely missing word here is intelligent, which, based on what we know about my cat, is probably true. Let's try it though with something a little bit more interesting to demonstrate this bias that I was just talking about. Remember, it's gone out there and it's learned from what's out there in the wild. So this next one, exactly the same thing again. I've changed the sentence to the man worked as a mask. Okay, so the man worked as a what? What does it think the man worked as? Let's run this again and see what it thinks. Here we go. So it's most confident it's carpenter, but it could also be waiter, barber, mechanic, salesman. Let's try that now for exactly the same sentence, but the woman worked as a. Let's see what it comes up with here. Nurse is the top answer. Waitress, maid, prostitute, and cook. Quite interesting. Okay, so we can see the little glimpses of the rubbishness and the bias that it's sacked on. So just be aware that when you're using this models like this, it's learned from stuff that's out there. Let's try the final one. The nurse tended to the patient and blank spoke to the doctor. Let's see what it predicts here. Top answers the pronoun she. Then I, then he, and they. But by far the most confident was she. So it thought that it just automatically assumed that nurse was a woman. So just be aware of that, and it's quite interesting to look at some of the stuff. And remember, it's just learned from what we, the human race, have put out there, and it's learned from all that bias and rubbishness. So there's some awful things that you can type in here that will give you some horrible results. So do bear that in mind. You should always have that in the back of your mind whenever you're looking to apply anything from a large language model. Okay, just before we move on to the exercise, we're about on time. I'm just going to just briefly mention Elmo. So about a year before BERT, there was another encoder model that made quite a splash at the time, known as Elmo, which stands for Embeddings from Language Model. And yes, there really is a Sesame Street running through. There was a reason why we had the Sesame Street themed songs at the start of this session. There is a Sesame Street thing running through large language models. So Elmo works a little bit differently to BERT. It doesn't use mass language modeling, blank, remember. It is bidirectional, but it's not bidirectional in the same way. So in BERT, it's bidirectional because it has a blank word and looks before it and looks after it and says, okay, I think it's that. The way Elmo works is it has a model for the text before a word and then a separate model for the text after a word, and then it joins those models together. But the problem is that doesn't allow for looking in both directions at the same time, and that's one of the things that gives mass language modeling in BERT its power. It can look in, so okay, here's the information I've got from before, and there's the information from after. Using those clues together, what do I think is the missing word? So that's why a key difference between BERT and Elmo. But nonetheless, Elmo was incredibly impressive as an encoder model, and could deal with polysemy just like BERT could as well. Okay, I'll stop talking there. We'll move on to the first exercise. I want you to take a 10-minute break though first. So make sure you take a 10-minute break, stretch your legs, and not think about Sesame Street or blankety blank for a moment at least. After that break, you're then going to split into your groups and give you about half an hour to basically have a play around with the two ways in which BERT learns. So remember, that's master language modeling, blankety blank, and next sentence prediction, which is where you predict whether one sentence belongs follows from another sentence or not. So for the master language modeling bit, you can either use that online API, the link in the earlier slide, or you can use the piece of code that I've given you that I just showed you running a moment ago, the BERT MLM.py. Hopefully you saw my message about the first time it runs that, it will do about a 500 meg download. So hopefully you are already run it, or if you're not, you might, and you're intending to run it, you might want to do that just before you go on your break, depending on your internet speed. You won't all have to do this. You're going to be in a group. I'd suggest one of you shares your screen so you can contribute in, because it may not work for everyone. Try different sentences with different words blanked out and see what BERT predicts. Maybe explore some of that bias that I was talking about too. So what insights might you be able to generate from some of that stuff? Now, for this particular PY file, if you're using the .py file rather than the online API, you'll need to use the BERT MC CPU environment. So make sure you're in that environment before you run that code. Just to flag up, the environment you just saw me using, it's called TF, but my environment names are slightly different because mine has got the GPU stuff installed. So that's why the environment names are a bit different to what you'll see on my screen. Then for the next sentence prediction bit, you can use the BERT NSP.py file. And that also requires around a 500 meg download, but it's the same one. So whatever one you run, it'll do that download, and you won't have to do it for the other one. So what I want you to do is read through the code in this one, in the BERT NSP.py as a group, and make sure you understand how it works. Okay. The code in here will be a little bit different because it uses PyTorch. Now we talked about PyTorch briefly earlier in the course. PyTorch is basically the main alternative to TensorFlow. We primarily use TensorFlow in this course. PyTorch is very good though as well. It works a bit differently. It's much more, you put everything together yourself and you build it up piece by piece, whereas TensorFlow via Keras, anyway, the API hides a lot of that from you. People have preferences as to which that, would you rather sort of get down and dirty and really understand all the nitty gritty, or would you rather have a simpler API? And there are pros and cons to each, but I flagged this up because some of the stuff you'll see in there will look a little bit different, and I've put comments in to explain how it all works and make sure you understand how that works. The reason it looks a bit different is because it's using PyTorch. So it's a slightly different approach, but can be used with either TensorFlow or PyTorch. Uses both. So read through the code and in this one to make sure you understand how it's working. It's a bit more than the 3 lines of code in the other one. Then run it and observe the output. So this is for the next sentence prediction. Try different pairs of sentences. Try some sentences where the second sentence does follow from the first. Try some where it doesn't. And see how well BERT performs. BERT will basically make a prediction. Yes, this sentence pair is a true sentence pair, or it's not a true sentence pair. Okay, so predict whether. So just like in the first one where you're peeling back the layers and having a look at the master language modeling bit, this allows you to peel back the layers and get into the next sentence prediction bit. But so for this one, because it uses PyTorch, you're going to need to use the BERT Torch CPU environment. So make sure you switch over to that environment if you are running this one. Okay, is everything clear? Any questions about any of that? Let's check the chat in case there's anything here. No, okay, in which case, right, so it's 10:40, go and have a 10-minute break, and then I'll open up the breakout rooms now. Hopefully you all saw the note about the breakout rooms, so I've basically doubled up the rooms, so join one of the 5 new rooms, depending on which your normal group is. I mean, we've only got very small numbers here today. I would suggest if you've got If you don't have a regular group, if you're joining from outside of HSMA, this round of HSMA, or if your group is too small, just join another group. Doesn't matter. Okay, so just join whichever group you like, but to be doubled up. Okay, let me stop sharing. I'll open the breakout rooms. We'll resume at 11:20. So go and have a 10-minute break, and then go into your rooms, and I'll float around. Okay, welcome back, everyone. So hopefully you've had a bit of a play with that. The next sentence of prediction seemed a bit weird, but other than that, the master language modeling seemed to be working quite nicely, which is good. So hopefully that gives you a bit of an insight into how BERT is trained. This isn't how we use it, but this is basically explains how the thing gets trained, essentially. So what I'm going to do now is I'm going to talk you through some code that shows how you remember we talked about you take a BERT pre-trained BERT model off the shelf, and then you would probably fine-tune your own model to then attach onto it for the thing you want to do, and that's what we're going to do here. So I'm going to talk you through one for a sentiment analysis. So share my screen. Where are we? Okay, so we're going to walk through this piece of code. This code is going to use the outputs from BERT. Remember, we've got the BERT pre-trained model has got all that sort of rich context information. We're going to use that and then fine-tune it to say, I want you to use that context information to do some sentiment analysis. And we're going to predict the sentiment of movie reviews, and we're going to use exactly the same data set we used back in the sentiment analysis training in phase 1. And in that training session, we built our own little model from scratch. So we're going to see how it compares, how BERT compares here. So the files we're going to be walking through are BERT Data Camp Tutorial Part 1 and BERT Data Camp Tutorial Part 2. You will not, unless you've got access to a CUDA-enabled GPU, you will not be able to run Part 1. Well, in fact, if you're on Windows, we've found out you won't be able to run Part 2 either, because of the issue with TensorFlow text. But assuming that issue, even if you didn't have Windows or it actually had TensorFlow text available, unless you had access to a GPU, you wouldn't be able to run Part 1. Part 2 would be fine because it just loads in the pre-trained model. But Part 1 is where we're going to do the fine-tuning. So I'm going to do it live because I have a very fast CPU and you can watch how fast it is. If you want, I was going to say, if you want some amusement, just hit run and see what the estimated time is, but it won't work because it TensorFlow text. So that you won't even be able to do that. Oh no, I'm talking through the code. Right, so let's switch over to the code. So BERT Data Camp Tutorial Part 1. So I'm going to talk through this now. Let's just make that a bit bigger. Now, as I talk through this, I'm just going to close that down. I'm going to set this thing running. Close that down. I'm going to set this thing running over here whilst I sort of start talking through it, because even on mine, it'll take about 5 minutes. Let's. Sometimes I need to reboot VS Code to do this. Let's see if that will work. I'm also hoping that, because it uses 95% of my GPU, so I'm hoping that doesn't cause immense issues while I'm connected to Zoom. We will find out. Let's see what happens. Seems to be running okay. Let me just let it get through to the bit we need. We'll start training. It's going to take a second actually to do that, so I'll start talking. So okay, so this is the fine-tuning bit. This is where we're going to take a pre-trained BERT model off the shelf, and we're going to fine-tune it. We're going to use that context information that is learned out there on those 3.3 billion words, and we're going to say, okay, I'm going to use this BERT model to do some sentiment analysis of movie reviews. So I'm going to train it a little bit on movie reviews and then use it to see if it can predict the sentiment of those movie reviews. So this tutorial, just flag up, I mentioned this link earlier, is from the excellent tutorial provided on DataCamp. I believe they are using something that is going to be deprecated next year, so be aware of that you will need to use updated stuff. That only happened as I was halfway through writing this, so just be aware of that. But it's a really good tutorial to read. One thing to flag up is that the link there will take you, in fact, I'm going to click the link. So that takes you through to this, and it talks you through and it has snippets of code as you scroll down like this. What isn't very clear and caught me out, it also has a link to the notebook in there, which I've also put a direct link to here, which will open it up on Google Colab, so you can run it on Colab. And all of you will be able to do this. You'll be able to run it on Colab. The only issue is that it doesn't make it very clear in this initial link, which uses the same code, that not all of the code is in here. So it forgets to mention that the notebook has all of the code, and this has most of the code, but not all of it. But if you're trying to copy it out and get it working, it won't work because there are bits missing. So just be aware of that. So you might find it easy just to follow the Colab link there. Okay, so I've adapted it slightly as well for our needs. So first thing we're going to do is our imports. As always, we're going to import the OS and shutil libraries. That we'll use these to do some file operations, some quite natty things that we're going to do in a minute. We're going to import TensorFlow as TF. We're going to use TensorFlow to do our fine-tuning of our BERT model. Remember, we can use PyTorch if we want to, but obviously you're all used to using TensorFlow, and that's what I'm used to using. So we're going to use TensorFlow, but you can use PyTorch. So if you learn PyTorch and you'd like to use PyTorch, then by all means you can use it. We're going to import TensorFlow Hub. Basically, TensorFlow Hub is a repository of trained machine learning models. We import it under the alias hub. You can see mine is now starting to run. So this is the fine-tuning training that's going on over here. We'll see what the code is that will be doing that. So you'll see here that it's doing them, it's taking just over a minute per epoch. There are 5 epochs. When Elliot tried this on his very fast computer, but not using the GPU, it was estimating an hour per epoch. That's the difference. That's why you need a GPU. Okay, you cannot do this without a GPU. Just won't, it's horrendous. So then we're going to import TensorFlow text, which obviously apparently if you're on Windows doesn't exist, which is slightly annoying. Let me just scroll that over. You can also use Keras NLP, which is an alternative. I wonder if that's on Windows. I've not used Keras NLP, so that might be worth exploring. And basically that TensorFlow text that you can't use is a library that gives you some low-level access to NLP models and utilities. Of course, you can use all this on Google Colab. The problem is for this exercise that won't work because you then have to you better run this code if you put this up to Colab. Remember, it's already got TensorFlow and everything installed, but you won't be able to do the exercise on Colab. You'd have to upload 2.4 gigabytes of files, which isn't going to work in the time frame. We're then going to, from official.nlp, we're going to import optimization. This is basically just to create our Adam optimizer, which you'll remember from previous machine learning training. We'll come back to that. And we'll import matplotlib so we can plot learning performance as well. So the first thing we're going to do here, this little line of code basically sets up the TensorFlow logger at the error level. Don't worry too much about that. That link will explain the different levels, but it's basically what information it logs, and this is set at the error level. So the first thing we're going to do is we're going to download, extract, and tidy this large movie review dataset. So you remember when we did this in the phase 1 training for the sentiment analysis session, I got you to do this manually. So you downloaded, you went to the website, you downloaded the large movie review dataset, and then you extracted it. And then some of you, because I forgot to mention it, some of you didn't delete the unsup folder, and then it causes all sorts of issues. This code's going to do all this for you. So it'll go to that link. It will automatically then download that data set. And basically it'll then specify we'll then tell it which the training set is, which the test set is, and all that. So we'll do that without having to do it manually. So this is basically what this is doing. It grabs the file, downloads it. It then sets up the file path. This is why we're using the OS library. And it will basically say, here's where the training folder is. It's in ACL, IMDb, and add on the train subfolder. That's basically what this is doing. So into your path, and then that becomes the training set. And this will automatically remove that unsup folder. Remember, that's the one that's used for unsupervised learning, which we don't need here. We're not doing unsupervised learning. But if you leave it in, it'll throw it off because it thinks there's another category called unsup. And it throws off your learning, and it's terrible. So this will basically delete that folder for you. This is what you did manually before in the previous training. This will do it automatically. We're then going to do something called setting up an auto-tune algorithm. Basically, what this does is it automatically prefetches data during the training, and it automatically optimizes it to your CPU performance. So it'll go and grab, while it's training, it'll go and grab more data ready so that it can, and it'll do that in line with how good your CPU is, to try and make it as efficient as possible for your computing performance. So then we're going to set up a batch size and a random seed for our training. Now, remember from the machine learning training, batch size is basically the number of training examples that we shunt through the network in one go. So we don't tend to put everything through all at once. We split it up into batches, and then we shunt them through. And then once we shunted through all of the data in batches, that's known as one epoch, once all of the data has gone through once. The random seed we're going to use so that when we carve up the training and validation data sets, we make sure that we don't randomly pick the same data to be in both. And that's important because so if we didn't have a random seed, then it would just completely randomly pick the things. And you could end up with the same data that you're training on that you then use as your validation set, which remember is the stuff that it sort of peaks at to adjust itself throughout the training to sort of test itself before you get to the kind of final test set to try and improve itself. So if we didn't do that, it would basically be looking like having an exam, having the answer to that exam, and then saying, oh, I was correct, because you've looked at the answer and your answer matches. So clearly we don't want that. So we set a random seed, and of course, being computer scientists and geeks, we always use the random seed 42, which is the meaning to life, the universe, and everything. So what we're going to do here, this should all look fairly familiar from your machine learning neural network training. So we're going to specify our training data first. We're going to carve off 20% of the training data to be a validation set, and we're going to give the location of that data, which is in the train. Remember, this IMDb data is already split into train and test folders, which is really nice. So we say here's where the training data is. It's in this subfolder here. And remember, if we look at that, you'll see there are lots of individual text files, and each text file contains a movie review. And they're further separated into positive examples and negative examples. We give the batch size that we specified above, so 32. So 32 reviews will be shunted through the network at a time. The proportion of the data we're going to carve out for the validation set, which is 20%, and the random seed. We're also going to specify that this subset is the training set that we're going to store in raw train DS. That'll be the training bit, not the validation bit. and we'll specify the random seed. That will make sure that whichever one's the 80% that we pick from that folder, the 80% of the reviews that we randomly take will not be none of those reviews will then feature in the 20% validation set. So you'll see all that's run over on the right hand side. We'll come back to that in a moment. If you were doing this without a GPU, you'd be probably still loading up the model. Then we're going to store the class names that identify the training data. Remember, this training data is nicely separated into POS and neg, so it's already got all of that, so we can grab that straight away. So it'll automatically split it into positive and negative data. Then we're going to set up a prefetch using this auto-tune thing we specified above. So basically, as I say, as the model's training one batch of data, the prefetch will go and grab the next batch of data ready, and it'll optimize that according to your CPU performance. So don't worry too much about that. This is basically just standard code that you can use to it just improves things a little bit. Then we'll set up the validation set, exactly the same as we did for the training set above, but this time we say this 20%, the validation set. So it knows that the 20% that we've carved out, it now needs to grab that 20% for the validation set. And because we've used the random seed, none of those examples will have been used in the training data. So we've carved it 80-20 and nothing is in both. Then we'll set up a prefetch on the validation data, exactly the same as we did for the training data. And then finally, we set up our test set, which we don't need to carve anything out of that. The test set will just use the whole thing. So we don't need to specify a split. We just need to say where it is and what the batch size is. We don't need a random seed or anything like that. We're not carving anything off. So that's all stuff that you've seen before. That's exactly the same, apart from the prefetches, as we did before in the training. So now the first thing we need to do is to select a BERT model. This is the encoder. So when we talk, it can be a bit confusing because there's lots of different types of model. There's the BERT model, which is the encoder. There's a pre-processing model, which pre-processes our data. We'll come on to that in a moment. There are fine-tuning models, which is what we're going to train it here. But remember, I said you can also grab those off the shelf. But there are lots of different types of models. So the BERT model, the encoder, is the big 3.3 billion word model that we're gonna use, that's been pre-trained on all that and has all that context information. So we're going to use the very original BERT model that was first presented in the BERT paper. And this is the link on TensorFlow Hub that takes you directly to that model. So as I said before, the uncased bit refers to the fact that it's basically been translated into lowercase for tokenization, so that it doesn't matter whether it's uppercase or lowercase, it just makes everything lowercase. It also strips out any accents above letters, things like that. This version of the model is hosted on TensorFlow Hub. Just to explain these little codes a little bit. So L12 basically means it's got 12 hidden layers in the model. Remember, hidden layers are the ones in between the input layer and the output layer. So the ones in the middle doing the hard work. It's got 768 hidden units. That's the H768. That's your neurons, and 12 attention heads. And those are the things that are doing the attention stuff for this. You can read more about it. So the nice thing about here, we give that link. We said this is the model I want to use. So I'm going to store that as TF Hub handle encoder. Here's the URL for it, and it'll download that model. But we can click on that link, and it'll take us through to the model, and it will explain how the model works, and the fact that this is the original model. There's the link to the original 2018 paper on BERT. So if you click on that, it'll then take you to the original paper, the academic paper that was published, that introduced BERT to the world. And it explains how you use it. It gives examples of how it can be used, how it works, etc., how the master language modeling works, and how you can access all of that. So for each of the models that's hosted on TensorFlow Hub, you can click on the link and it'll explain how that particular model works. Okay, so the download that does the first time you do this is it's downloading, when you run this, it'll download, if you haven't already got it, the 389 megabyte file, which is the pre-trained BERT model. So as well as that, we also need a pre-processing model. And the pre-processing model is the one which is going to convert our text into numeric data. Remember, we have to put it through the network in the form of numbers. And it'll also shape them into tensors. Remember, we need to, for a neural network, we need everything in both numeric form and then stuffed into these things called tensors, which are the shape of the things that get stuffed through a network. So here we're going to use, so the different pre-processing models we can use. Here we're going to use the BERT-N, N just means English, uncased pre-process model. Different BERT models have different pre-processing models. So this is the one we would use for this model, this BERT model, the original BERT model, but there are different ones, and the documentation will tell you which ones you should use. So you can have a look at that link that I just showed you, and that will explain what pre-processing model. In fact, it'll be under advanced topics. So if I click back on that link, so this is back to the original BERT model, under advanced topics, pre-processor documentation. If you click on that, it will then link to the pre-processing model that you should use for that one. That's the BERT-N uncased. You can see that link there. That's the one we're using. Okay, so it seems complicated, but actually it explains everything that you need to do. If you're using the original BERT model, this is what, and you're doing it in English, and you're not worried about the case of letters. So in most cases, this is the combination you would use, but you can use other ones as well, and it'll explain how to do it. So we've loaded our BERT model into TF Hub handle encoder, and we've loaded our pre-processing model, which will turn the raw text into numbers and pre-process it and stuff it into tensors. That gets loaded into this TF Hub handle pre-process. So we're then going to load in the pre-processing model that we've just we selected up here as a Keras layer. So we're going to load it in as a layer of a neural network, and we're going to try it out on some sample text to see what it does. Okay, so I'm going to set up a little neural network layer here using Keras. Remember, Keras is just the API for TensorFlow that makes things easier, so we can talk to it in normal language rather than very complicated language. And we're going to pass in the pre-processing model that we've downloaded up here. So then we've set up this pre-processing model. We're just going to look at the pre-processing model for a minute. I've got some test text. So here's my test text. This is such an amazing movie. And then I'm going to apply the pre-processing model to the test text. Now, obviously, I've already run all this. So let me scroll back up to where it did this. Is it here? Find where it is. Yeah, it's here. Okay. So this bit applies that pre-processing model to that. Oops. Oh, sorry. Oversensitive mouse. To this piece of text that we've got here. Okay. Then what we're going to do is have a look to see what it did. So we're just using the pre-processing model. We haven't used the BERT model, just the pre-processing model. We're going to look at just the first 12 tokens that get generated by the pre-processing model. Now, in this particular model, there are 128 tokens that are generated for each piece of text. And you remember from the natural language processing training, everything that gets fed through a neural network has to be the same shape and size. So for text, that means that you have to have text of the same as numbers going through with the same length. Now, obviously, all movie reviews can have different lengths. So the way we do that is we decide on a length, and then everything that's longer than that gets chopped off, and everything that's shorter than that we pad out with this special pad token. Okay, everything has to be the same length. So that's why when we look at this here, so if we have a look, we can print out the keys from the pre-processing model. We see there are there's a dictionary that's generated. It's generated 3 different keys. One's called input type IDs, one's called input mask, and one's called input word IDs. And we can see the shape as given as 1 and 128, and that's the 128 tokens per piece of text. Let's have a look at these things in order. So the first things are the input type IDs. That's basically your sorry, that's not, that's in the wrong order. It's the input word IDs. So that's what we've got here. So these are basically the numerical representations of our words, but they're not just, so they're numerical representations of the tokens of our sentence. Remember, our sentence is, this is such an amazing movie, exclamation mark, okay? These are that's the numerical representation of that text. It's not just individual words, it also includes punctuation. So there is a numerical representation of the exclamation mark, and it also includes a token for the start of the sequence and the end of the sequence. And in fact, you can also have a situation where you have multiple tokens for one single word, where you have different morphemes, where you got morphemes are like syllables, but they are semantic syllables. So it's where you have, without going into it too much, is with it, you've got different types of meaning associated, different bits of the word. Don't worry too much about that. It uses that so that it won't have seen every word. Well, hang on, the word, I don't know, running, that's like the word run, which I have seen. It's probably seen the word running, but there we are. So that's why you've basically got a 6-word sentence here. This is such an amazing movie. It's only 6 words, but if we count them here, we've got 9 tokens. Yeah. So that's why. It's because we've got a start token indicating the start of the sequence, 101, 102 indicates the end of the sequence, and 999 is the exclamation mark. So these are the words. So 2023 is the number assigned to the word this. 2003 is, etc. Okay. And let me just shrink that down a bit so you can see it a bit more. Need to find where it is again. There we go. So you can see there are also, because we're looking at the first, we're only looking at the first 12 tokens. There are 128 of them, remember. So if I hadn't have put this bit in here, this would be 128 tokens long, but most of it would just say 0, because we've only got a 6-word sentence, but we need it to all be the same shape, and we've decided that they should all be 128 long. So we'd have a lot of zeros, which are our padding for that particular sequence. Then if we look at the first 12 of the input mask, so basically the input mask has a value of 1 for all of the positions where there is an input token, and a value of 0 for the padding tokens. Okay, so here the first 9 are where we've actually got input and the rest is padding. So again, we're only looking at the first 12. If we looked at the whole thing, there'd be 128 entries here, and only the first 9 would have 1s and everything else would be 0s. And then finally, we've got the type IDs. The type IDs basically have a 0 or a 1 for each token, depending on the segment to which the token belongs. Now, we don't use that here, that you'll just see 0s on this particular example. But it is used to identify whether the particular token belongs to a question or the answer, because remember, BERT can be used for question and answer generation, for example, or where in the next sentence predictions, you'll have seen in the BERT nsp.py file, looking through that code, that when you ran that, it had some had 0s, some had 1s. The first sentence has 0s, the second sentence had 1s. So it identifies this token belongs to from sentence A, this token belongs to sentence B. But we're not using that here, but it still generates. Okay, so that's basically what the pre-processing model is doing. So it takes our raw text. This is such an amazing movie in our case. And if we apply the pre-processing model to that, we can see what it's doing. And in this case, it was it's generated this sequence of numerical tokens, this set of input masks, this set of type IDs. That's what it does. Okay, so now let's move on to writing the function that will build our classifier model. the thing that's going to, the fine tuning bit, the thing that's going to, we're going to use to train the raw outputs from BERT to conduct some sentiment analysis of movie reviews. So the way we do this differs according to the BERT model we've picked. So again, you should have a look at the URL and it'll explain how you should build up a classifier model to fine tune it. Okay, so all of the stuff is in the documentation. And that's, you can find all that in the basic usage section. Now, we're going to use TensorFlow. We're not going to use PyTorch, but we could, because we're used to using TensorFlow on the course. We're going to be using Keras, because we're used to using Keras as the API to interact with TensorFlow. But this time, this is going to be new. We're going to use something known as the Keras functional API rather than the Keras sequential API. So the sequential API is the one you've been used to using so far. So when you build, when we've been building up neural networks, we build them up a layer at a time. We say, okay, I want an input layer like this, and then I want a hidden layer, and then give me a dropout layer, and then give me another hidden layer, and then here's my output layer. Bung them all together. You build them up one by one. Okay, that's how we've done it so far. But you don't have to do it like that. You can use the functional API. And the functional API basically allows you to build up models that are non-sequential, non-linear, or which have got multiple inputs or multiple outputs. Okay, we'll see this in action in a moment. So if you want to read more about what the functional API is compared to a sequential API, there's a little link in there, and you can read more information about how that works. But it's basically different to the sequential API, which you're used to using, where you just say, give me a layer of this, then followed by a layer of that, followed by a layer of that, etc. We do it a bit differently here. So we're going to define a function that will build one of these things. So I've called it build classifier model. So the first thing I'm going to do is I'm going to set up an input layer that will take in the raw text before it's pre-processed. So the original raw text. So that will set up an input layer for us here. Then I'm going to set up a pre-processing layer, much as I did in the example, the little example I did above, which we used to see what it was doing. I'm going to set up one of those. I'm going to take the pre-processing model that I picked up above. I'm going to set that up as a Keras layer, just as we did before. And I'm going to say, okay, so you take in the first layer of the network, will take in the raw text, and then it's going to shunt that over to a pre-processing layer. And the pre-processing layer will then basically turn it into numbers and into those tokens and give us the type IDs and everything we've just seen. So then we're going to apply the pre-processing layer to the raw text inputs we read in to generate the inputs for the BERT model, the encoder. So we're going to use something called a layer call here, and this exemplifies why we're using the functional API of Keras rather than the sequential API. So this is where it differs. So here, what we're going to do is we're going to use something called a layer call, and basically it tells TensorFlow that we want the outputs of the layer that we put in brackets to feed into the layer that's outside of the brackets, and the outputs of that will be referred to by this name that we give before the equal sign. Okay, so it's a bit like drawing an arrow from one layer to the next and linking them up. So in this example, we say we want our text input layer. Remember, that's the one that we chuck in the raw text as text. We want that to feed in to the pre-processing layer. So we're like drawing an arrow between them. And the pre-processing layer, the outputs of that will in turn feed in into an encoder inputs. We'll refer to them as encoder inputs because that's going to feed into our BERT model. Okay, so text input goes into pre-processing layer, and the outputs of that layer will refer to as encoder inputs. This will all make much more sense when you see that we can get it to draw a little diagram in a moment, and you'll see how this works. Then we're going to set up a layer that will use the BERT encoder model, the main big BERT model, the one we specified earlier. Remember, we're using the original BERT model. And we specify that this is trainable because we're going to do some fine tuning on it. So we want the model to adapt as it learns, basically. But this is the fine tuning bit. So we need to flag up this is a trainable layer. So we set this up and we say, give us a Keras layer, and it's a trainable layer, and the name is going to be BERT encoder. And the thing I'm stuffing in that layer is the TF hub handle encoder, which, remember, is what we that's where we've downloaded our BERT model. It's in there. So just as we did above, we're then going to set up another layer call, and we're going to say the encoder inputs, which, remember, these are the things that have been, we've pre-processed the raw text, and the outputs of that pre-processing are stored in encoder inputs. Now we're going to say encoder inputs feeds into the encoder, that's the BERT model, and the outputs of that, the BERT model, we'll refer to as outputs. Okay, so we're drawing arrows between these things. Now we're going to add some additional layers, which we're going to build up and store in something called net. First, we're going to specify a layer that will take the pooled outputs of the outputs generated by the encoder layer, the thing that's using the BERT model, up above. So you've seen a little bit of pooled outputs before. Pooled outputs basically simplify, they kind of simplify the outputs in some way. What they're doing here, the pooled outputs will have a single representation for each input sequence, i.e. each piece of text, each movie review in our case. Whereas sequence outputs, which is kind of the opposite of pooled outputs, would have a representation for each input token, i.e. each word, each punctuation, the start and end sequence tokens, etc., etc. So the BERT model we're using is the original BERT model, and we saw that it had 768 hidden units, which means it is a 768 dimensional model. That's where it starts to get conceptual. Which means that we would have a 768 dimensional representation for each sequence if we're using a pooled output. So for each, think of sequence as review in this case, or for each token if we were using a sequence output. So we're using pooled output, so we've got 768 dimensions per movie review, as opposed to 768 dimensions per word of each movie review. Okay, we don't want that. We want the per movie review. You typically use a pooled output when you're trying to classify text. That's what we're doing here. We're trying to classify text as positive or negative. That's what sentiment analysis is. Or if we're measuring similarity between sequences, so i.e. how similar is this piece of text to this piece of text. So you can use that for things like you know, plagiarism detection, things like that. So I'm just going to shut my cat out. Sorry, it's me. Sorry about that. Okay, so pooled output for the most of the stuff you'll be doing is more common. There's some explanations here which quite nicely explain the difference and how this works. So we're going to use pooled output, okay? So we're going to start by building up our network by getting the pooled outputs from the encoder. Remember, the encoder is the BERT model. That's the thing that's generated all of that stuff that we want the encoder to do. So all the context information, all of that, okay? So basically what we've got, we're going to join that into our network. So this first bit, we've now got a network that has raw text flowing into the pre-processing model, which will turn it into numbers and do the other pre-processing stuff, strip out the accents, all that kind of stuff. That then flows into we've then got pre-processed text, which will be numbers, which will then flow into the encoder model, which is the BERT model, which will generate encoder outputs, i.e. that's the context information, all that rich information that's come out of the BERT model. And then we're going to pool those encoder outputs to make them more manageable to use. Okay, that's what that line of code is doing, essentially. It's adding into our network that pooled output. Because remember, outputs is linked up here to the encoder. In turn, it is linked to the encoder inputs, which in turn is linked to the pre-processing layer, which is linked to the raw text. It's all the arrows we've drawn between them. What's my arrow? There we are. Then we're going to link the pulled outputs layer that we specified above to a dropout layer with 10% dropout. Now remember from your neural network training, dropout basically randomly switches off a percentage of the neurons in our network by changing the weights coming out of those neurons to 0. That's the way it does it. It says switch off those links or make the weight 0, so it ignores those neurons during a particular training epoch. And remember that we use dropout to try and prevent overfitting, because what we're doing by using dropout is we're stopping the model from becoming too reliant on a particular area of the model, that it gets obsessed with a particular area. So we use dropout to stop that, to say, well, there's no point getting obsessed with, you know, the fact that this bit's important, because we might randomly switch that off, and it stops the overfitting, that it stops it trying to find something that actually may be too specific to the training data, and it actually isn't very generalizable. Okay, so that's basically what we do. We use dropout for that reason. So we're going to switch off 10% per epoch, randomly pick 10% of the neurons in the pulled output layer to switch off per epoch during our training. So we'll add in this dropout layer here, and because we're using the functional API, we again use this layer call format where we say net is joined onto dropout layer. Okay, draw an arrow between them, and then we're going to add one final layer onto the network, which will basically just be a single node that will represent the final output of the model, i.e., in this case, our classification is the review positive or negative. Remember, BERT models don't have a decoder, only an encoder. So we have to build on all this stuff. It's just got the raw context information with something with. So we're going to use that raw training or that raw potential to do some movie review classification, but we can use it for building a chatbot if you wanted. So the layer we're going to set up as densely connected. Remember, that means that all of the nodes from the previous layer link into it. We're not using an activation function here, which means that we're going to need to feed it through a sigmoid function in order to translate something between 0 and 1. So the output's between 0 and 1, so that we can interpret it as a likelihood of it being positive or negative. But we're going to do that separately a little bit later here. So once we've joined that up using a layer call again, so we join that to the existing network that we've built. And then we finally return our assembled model. So when we build a model using this functional API, rather than the sequential API we've been used to using, we basically start from an input, which in our case is raw text input, and then we chain together the layers of the network we defined above as the model's output. So that's why we've got this form here where we return the model in the format model and then open brackets input and output. Input is the text, the raw text input. Output is the network we've built up. Okay, this will make more sense when you see the diagram in a moment. So that's the function that we've written to build up our classifier model. Obviously we won't do anything until we call it, so let's call that function. That will then build a classifier model. And we can use a little command in the IPython console to have a look and it'll automatically generate a diagram of what our model looks like. So all that confusing stuff that I've just talked about, let's see what it looks like. Okay. If you want to do that yourself, you'll have to install PyDot using pip install PyDot, and also GraphViz by downloading it here. And then you input this command here into the IPython console. Because once the code's run, so obviously my code is run, so I'll paste that in. And if I do that, oh, Control Enter. Oh no, Shift Enter. Okay. So you can see what this does is a neat little thing. It draws out. Basically, this is what our network looks like. So we've got a text input layer. That's our raw text. That then goes through to a layer called pre-processing. That then goes, that's the one that's going to do turn it into numbers and do all that other pre-processing stuff. Then that feeds into a BERT encoder. That's our BERT model. That then feeds into a layer called dropout, which is going to randomly switch off 10% of the pooled outputs here. And then that'll feed into the classifier layer, which will basically say we can use the output of that to determine whether we think the review is positive or negative. Okay. So that's built our model, but obviously now we need to train it. So the BERT model has already been trained. We're using a pre-trained model. It's gone out, and we're not going to redo all that 3.3 billion words of training. But we can add to this for our particular application area. That's the fine-tuning bit. And we're going to do that using the IMDb data we downloaded. So that's the same data we used in the sentiment analysis training. In that training, we built a neural network from scratch. We didn't use a BERT model on to sort of get us going. But here, we're using the BERT model to start us off and then just fine-tuning it. So we're going to specify our loss and function and the metrics we want to capture. Again, all fairly standard stuff for neural networks. Here, we're going to use a binary cross-entropy loss function. You'll remember, hopefully, for the training, that we use a binary cross-entropy loss function where we have a classification network. This is a classification problem. Do you belong to class A or class B, positive or negative? And we've got two possible classifications, positive and negative in this case. And we're generating a probability that an example belongs to one of them, probability that is positive or negative. Okay. You'll also remember that from logic equals true, basically just means that you should normalize the outputs. They fall between 0 and 1, and therefore we can interpret them as a probability or likelihood, I should say. Okay. So remember, hopefully you'll remember the loss function is basically the function that we use to calculate error. Remember, error is called loss in a neural network. We also need to specify the metrics that we're going to use to capture model performance. For simplicity here, we're just going to use accuracy, but hopefully you'll also remember there's all sorts of things that you'll want to look at if you're doing this for real, to see how well your model is performing. Just looking at accuracy on its own can be very misleading. But we're just going to use accuracy for simplicity here. Here we're going to use something called binary accuracy. This is actually identical to accuracy. Remember, accuracy is just the proportion of times we predicted correctly. So the proportion of times we correctly predicted out of total number of predictions. The only difference is binary accuracy also allows us to optionally specify the classification threshold. So you'll remember that by default, if the output number comes as above 0.5, we say it belongs to class 1. If it's below 0.5, it belongs to class 0. So in our case, class 1 is positive review, class 0 is negative. By using binary accuracy, we can actually change that threshold. And that can help us if we've got a lot of data that's biased towards one or the other. We can help sort of fine tune it a little bit. We're not going to do that here, but if we did want to do it, do that, and you can talk about that at this particular link here. We're then going to specify that we want 5 training epochs. Remember, an epoch is just where you've one epoch represents when you've shunted through all the data in batches once. So we're going to have 5 training epochs. These are the things that on my GPU take a minute per epoch, and if you're not using a GPU, will take several hours even on a good one. Then we're going to a little bit more complex than perhaps it is. Remember, we can adjust the speed at which a neural network learns, which is known as the learning rate, because and it's basically the amount that we sort of push it along the line. And we don't always want it to learn very quickly because it can miss stuff. We're going to use the same learning schedule as was used for the initial BERT training outlined in the original BERT paper. And I don't want you to worry about the details about it too much, but basically it's going to use something called linear decay of a notional initial learning rate, which sounds very complicated. Basically what it does is it has a linear warm-up period. So the first 10% of training steps, it counts that as a warm-up, and it just uses a linear learning rate there. So basically what it does is it warms up to a faster learning rate and then gradually slows down as it fine tunes. So initially it sort of runs out the gate and starts learning really quickly to try and accumulate information. And then gradually it starts slowing down as it fine tunes. It's a bit like, for those of you old enough remembering fine tuning a television, you kind of tune your, to get to a picture of some sort and then start making smaller adjustments to get the nicest picture you can. It's a bit like if you go in the shower, you turn on the temperature, you might get it to, get it roughly where you want it, and then you gradually sort of fine tune. It's basically doing the same thing here. So to do all that and specify this warm-up period, which is going to be 10% of the training steps, we need to calculate the total number of training steps so we can work out what 10% of them is, okay? Because that's going to be our warm-up period. To do that, first we're going to calculate the number of steps per epoch, which we can find from the cardinality of the data set. Remember, that's our training data. Basically, that will just return the batch stop size of the data set. Remember, we split into batches, and the .numpy thing here will convert that output into a numpy array because the output's going to be a tensor. So that will put it into a numpy array so we can handle it. And then once we know the number of steps per epoch, we can easily calculate the total number of steps in the training, because it's just number of training steps per epoch multiplied by number of epochs. That's how many training steps you have. And then, of course, we can easily calculate 10% of that just by multiplying that by 0.1. And that will give us our warm-up period. We cast it as an integer because we can't have a fraction of a training step. So if that turns out to be a fractional number, we'll cast it as an integer. Then we're going to specify the initial learning rate that we want, the one that will start as, and that will change during the warm-up period and then subsequently after that. So we're going to use a smaller learning rate for this fine-tuning than the initial BERT model training, because we're not doing the big 3.3 billion word training. We're just doing a bit of fine-tuning training here. And the original BERT paper recommended this particular learning rate for fine-tuning. This is what they did when they fine-tuned. So that's what we're going to use here. We're going to use a value of 3e to the minus 5, which is basically just 0.00003. That's our learning rate, our initial learning rate. We're then going to set up the optimizer with the information that we've calculated up above. Remember, the optimizer in a neural network is basically the correction algorithm that decides how much to adjust each weight, both in terms of by how much and in what direction. Should I increase the weight, decrease the weight, and by how much? Based on the loss that's been calculated and back propagated through the network. That's, remember, blame assignment. So it works out, a neural network works out how far off was I, what's my loss, in other words, what's my error, and you then have blame assignment that gets the back propagation says, hey, you over there, you were responsible for me getting that wrong, and you were also responsible, but not quite as much. And then the optimizer basically comes in and adjusts the weight based on that blame assignment. The optimizer we're using is ADAM. Remember, stands for adaptive moments. As we said before, it's now the most commonly used optimizer. And of course, if in doubt, use ADAM, the old adage. So if you're not sure which one to use, ADAM is a good call. And we're going to use ADAM here. The original BERT model was also trained using the ADAM optimizer as well. So we're keeping it all in line. So we're going to create our optimizer. We specify the initial learning rate. That's that value we put up here, which is in line with what the BERT paper recommends for fine tuning. We calculate the number of training steps. We put that in here. The number of warm-up steps we put in here. And the fact we want the ADAM optimizer. So then we'll compile that classifier model that we created earlier. And that's the one that we built using the function that we wrote. And we're going to compile that model with this optimizer that we've just specified here. And we want our loss function that we specified above and our metrics that we specified above. So remember, we're using a binary cross-entropy loss function, and we're calculating binary accuracy. Okay, so that's set it all up, and then it's just time to train the model. Remember, or we refer to it as model fitting when we're doing neural networks, because we're trying to fit a model, fit a line in multi-dimensional space to our data. So we're going to specify our training set, our validation set, and the number of epochs that we specified up above. And we're going to store all of that in the training in an object named history, and that will allow us to look at the training history as it trained over time. So just a little print message saying we're training the model with, in this case, it's the original BERT model. And then I'm going to call the .fit method of the classifier model with that information that we've passed in. So here's my X, that's my training data. Here's the validation data set. And we remember we carved all that up above. And I wanted you to do it for 5 epochs we specified above. So then that's basically the training. We'll then see how well our trained model performs on the test set. So we're going to look at both loss and remember we want loss is error, so we want that to be low, and accuracy, which we want to be high. Okay, so we want low loss, high accuracy. And we can also, because we stored the training data in a dictionary, we can have a look at how that changed over time. So we can grab it out and we can plot that. I won't go through all these bits, but you can basically using matplotlib to plot the loss and accuracy on both the training and the validation data over time. And then finally here, I'm going to save that model so I can use that again. And that model is how I saved the model that I then transferred to you using Dropbox transfer. Okay, so I ran this obviously earlier, so let's see how well it performed. And we scroll up past the messages. So that's where it was training. Those are the 5 epochs of the training. Then it checks itself against the test set to calculate this. So we got a loss of 0.585 and an accuracy of 88%. So not bad. Seems pretty good. But if we look at the training over time, the plots, we can see here, so this is loss, the top graph is loss, that's error, and the bottom graph is accuracy. So if we look at error first, remember we want error to be low. The red line is the training data, the blue line is the validation data. We can see training loss is gradually getting lower and lower and lower, it's getting better, which we expect to see. Validation loss, though, is gradually increasing. What does that indicate? Any more? So we've got the error is gradually getting lower and lower, in other words, better on the training data, but on the validation data, it's gradually getting worse. What might that indicate?
Is that overfitting?
Yes, exactly that. So basically what it's doing, it's getting superb at the training data. And if you let it run long enough, it'll be 99, even 100% accurate, because it learns everything about the training data, but it then becomes largely useless for anything else because it's just learned all the intricacies of the training data and hasn't learned the more generalizable things. And that's it. That's the fine balancing act. Whenever you're doing machine learning, you want it to learn enough about the training data that it captures the things that are generalizable, but not so much that it's just now learning stuff that's just unique to the training data. Okay, so that's what we're seeing here. We're seeing a bit of overfitting. We see that on the accuracy too. So accuracy starts off about 80% on the training data, goes up to nearly 100% after 5 epochs. So not very long. But we're flatlining on the very quickly on the validation data. It's not getting any better because it's now just learning stuff that's just unique to the training data. Okay, so that saves that model. This second part of that will basically code will load that back in, and it's just got a simple piece of code that asks the user so I gave you 2 different models. I gave you a 5 epochs model and one that was trained as a 2 epochs model. So acknowledging that there was a bit of overfitting, maybe let's only train it for 2 epochs. So it'll cut off here instead. See if it's if that helps things a little bit. Obviously, there's lots of things you can do, but that's just a simple blunt force instrument that can help. It'll then load that model back up, and then we'll test it out. Our trained model, our fine-tuned model, to see how well it performs on these examples that I've just made up here. So let's run that. I think it's going to say it's exhausted. Oh no, maybe not. Okay, so specify the number of epochs. That's I've got both pre-trained, so I'm going to specify 5. I'll just load in the 5 epochs model. Let's have a look, see what it generates. It'll take a second to run that. Yeah, I thought that was going to happen. Right, let me just close down VS Code and reopen it again. Unfortunately, the GPU is exhausted, and I know how it feels. Let's run that. 5 epoch model. Should work this time. There we go. Right. So that's basically loaded back in. So it's loaded in the fine tuning that we've done and attached onto the big BERT model. Okay. Let's have a look at the 5 sentences. These are the same 5 sentences, I think, that we used for the sentiment analysis training. A fantastic movie that really pushed the boundaries of storytelling. Makes that one's positive, and it's very confident about that. It seems to make sense. The movie was really good, but I think sometimes it drifted. It's positive, which is right. Although it was very confident about that, and it might be a little bit more middle of the road. The movie was mediocre. There are far better films out there. It's very confident. That's negative. I thought it was okay, but not what I expected. It's pretty confident that is negative, which I probably agree with. This is the worst thing I've ever watched. Is incredibly confident that's negative. Okay, so it's done a pretty good job. That one's maybe a little bit more questionable, but it's done a pretty good job here of picking out what is positive and what is negative, and the kind of the confidence levels it has seemed to tally with what we've seen. But of course, we could load in the 2 epochs model as well and see how well that performs. So, I mean, we're almost out of time anyway. So, obviously, you're not going to be able to do the exercise that I had set, but I'll just very quickly show you what you would have done, and I'll show you the outputs from it. So, what you were going to do was to load in the BERT model trained over 5 epochs, the one I've just trained live, as well as one that was only trained over 2 epochs. Those are the ones I transferred to you, those big models. And you were going to compare that against the neural network model that we built back in the sentiment analysis session. And I was going to get you to try different movie reviews and see how well BERT seemed to do compared to building a neural network from scratch. Obviously, you can't do this if you're on Windows because it appears TensorFlow text is not available, which you need. But here, just in case anything went wrong, I did put this up in preparation. So here, for reference, this is the old model that we used, the non-BERT model that we used in the sentiment analysis training. That's this, and we're going to use the same example to test it. This review here, fantastic movie that really pushed the boundaries of storytelling. So the old model, on the test data, it was getting about 30.31 loss. It was about 86% accuracy. Okay. And it predicted on this test sentence, on this test review we gave it, it predicted it was positive, although it wasn't that confident. Remember, the threshold is 0.5. Wasn't hugely confident. Whereas I think if we were looking at that, we'd say, fantastic movie that really pushed the boundaries of storytelling. We'd be very confident that is a good review. Okay. Let's compare that to how BERT deals with this. So BERT, remember, it's the same training data, exactly the same training data, and the same test data. So accuracy is a bit better. It's about 89% compared to 86%. So it's quite a bit better. This is on the 5 epoch version. Loss is higher though. It's getting a bit. It's slightly higher error rate. But let's look at the example and its confidence. So using that same example, in all cases, it classifies it as positive, but it's super confident this one is positive, which tallies better with what we're seeing here. And it's because it's learned much more about context. So the fact that it knows much more about a fantastic movie that really pushed the boundaries of storytelling, the thing that's pushing the boundaries of this fantastic movie, it can associate all this much better. It's got all that rich context information than the the neural network we built from scratch, which is basically just looking for some. Oh yeah, I saw the word fantastic. Pushed maybe is positive. It's getting little clues like that, but it's not understanding that sentence as a sentence where it's saying this is a really, really good movie that is actually pushing boundaries. It's so good. The original model isn't doing that. The BERT model is, and we see that here. And of course, if we can see our fine-tuned model here is clearly overfitting, and we probably need to do a bit more than just reducing the epochs. But just as a first step, we've reduced the epochs, and actually that improves things a bit. We get better accuracy, and we get better loss. Loss is much lower. In fact, we've got lower level of loss than we had in the original model, and we've still got a very confident classification that this is positive for that review. So that's helped a lot. So if we compare this model to this model, actually we're getting much better accuracy, we're getting a little bit lower error, and importantly we can see the impact of having context information as part of that learning, that it's much more confident, and the idea of the exercise was to get you to try different things that are a bit more nuanced reviews to see if it was a bit better at picking things up than the original review. The original model. Okay, I will stop there because we're pretty much bang on. Let me stop sharing. Hopefully that was useful for you, and gave you a bit of insight into how BERT works, and hopefully, although it's a very complex structure, hopefully that's peeled back a little bit more about how this thing actually works under the bonnet. Remember, it's basically blankety blank with some next sentence prediction going through an encoder, which is basically extracting. It's a complex neural network that's extracting all this context information, and it uses that. We can then use that rich context information to do this fantastic natural language processing stuff. So the next time you interact with ChatGPT, you'll understand more about how the transformer architecture works underneath, because it all started from BERT. Any questions before we close off? No? Great. Okay, in which case, thank you all for coming along. And obviously don't forget it's the Learning Set meeting tomorrow. So those of you on projects, come along to the Learning Set meeting tomorrow, and I look forward to hearing about how your projects are progressing. Brilliant. Thanks, everyone. Bye-bye.
Thanks.
Thank you.